In this example, we're asked to find simplified expressions for s sub 0, s sub 1, and s sub 2 if we are defining s sub k to be the sum of 1 to the k power plus 2 to the k power plus 3 to the k power plus 4 to the k power plus dot 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 plus n minus 1 to the k power plus n to the k power. So let's go ahead and figure out what s sub 0 is. If I plug in 0 for all of these exponents, I would have 1 to the 0 plus 2 to the 0 plus 3 to the 0 plus n minus 1 to the 0 plus n to the 0. And all of these end up evaluating to be 1. And the number of times that this 1 is being added to itself is n times. So in other words, this is equal to n because 1 times n is n. Now let's go ahead and find a formula or simplified expression for s sub 1, which is essentially the sum of the first n integers or n positive integers. So I have 1 to the 1 power plus 2 to the 1 power plus 3 to the 1 power plus dot 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 plus n minus 1 to the 1 power plus n to the first power. So all of these things end up just being themselves. So we have 1 plus 2 plus 3 plus dot 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 plus n minus 1 plus n. So again, s sub 1 is essentially the sum of the first n positive integers. And the way that I'm going to come up with a formula for this is I'm going to do something where underneath this, I'm going to rewrite s sub 1, but I'm going to rewrite it in descending order. So my first term would be n, my next term would be n minus 1, my next term would be n minus 2, and so on and so forth. And then my second to last term would be 2, and my last term would be 1. Now, what I'm going to do next is I'm going to go ahead and these two equations that I have here, I'm going to add them together. And so on the left-hand side, I have s1 plus s1. So that's going to give me 2 times s1. And then on the right-hand side of my equation, I purposefully wrote them in this order so that when I add up and align them vertically, n plus 1 just gives me n plus 1. And then my next vertical alignment, if I add up n minus 1 plus 2, that also gives me n plus 1. Same thing for my next set. I have n minus 2 plus 3, which simplifies to n plus 1. And this will continue on for all of the vertically aligned terms. So I have plus dot 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 plus n plus 1, and my last term would also be n plus 1. And so this is appearing n times. So at this stage, I have 2 times s sub 1 is equal to, the right-hand side is going to end up simplifying to n times n plus 1. From here, if I wanted to solve this equation for s1, I could divide both sides by 2, and we end up getting n times n plus 1 over 2. So that is our formula for s sub 1. Okay, so lastly now, we are wanting to find a formula for s sub 2. And s sub 2 is equal to 1 squared plus 2 squared plus 3 squared plus dot 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 plus n minus 1 squared plus n squared. Now, unfortunately, we can't really use the trick that we used to calculate s sub 1, because if I rewrote s sub 2, if I wrote it in descending order, unfortunately, if I added that vertically, n squared plus 1 quantity squared is not equal to n plus 1 quantity squared like that. So trying that approach isn't actually going to help us in this instance. So we need to take a different approach. So it may not be immediately clear where this formula is coming from, but I'm going to somehow end up using the formula k plus 1 cubed minus k cubed. And I'm going to go ahead and simplify that at this point. So I'm going to expand k plus 1 cubed, and you can kind of FOIL that or multiply that out however you want. I'm going to use Pascal's triangle. So I have k cubed plus 3k squared plus 3k plus 1, and then minus k cubed, and that's just coming from this k cubed here. And then if I simplify that, what's going to happen is these k cubed will cancel out. So I get 3k squared plus 3k plus 1. And I'm just going to rewrite the left-hand side. Okay, so how are we going to end up utilizing this formula? Well, this is an identity, which means that regardless of what value I plug in for k, the value on the left side and the value on the right side should be equal to each other. So I'm going to go ahead and plug in a bunch of values for k and see what we get as a result. All right, so I have this pink formula or identity up above, and an identity means that regardless of what values I plug in for the input value, the left-hand side and the right-hand side are going to be equal to each other. And again, it might not be immediately clear how we're going to use this identity formula, but what I want to do now is I want to evaluate this for various values of k. So let's start off by letting k equal 1, and if I do that on the left-hand side of my equation, 1 plus 1 is 2 cubed, and then minus 1 cubed is equal to 3 times 1 squared plus 3 times 1 plus 1. Okay, now let's see what happens when we plug in 2. I have 2 plus 1 is 3 cubed minus 2 cubed is equal to 3 times 2 quantity squared plus 3 times 2 plus 1. When k equals 3, I have 4 cubed minus 3 cubed is equal to 3 times 3 cubed plus 3 times 3 plus 1. So when k equals 4, I have 5 cubed minus 4 cubed is equal to 3 times 4. Oops, this up above should be a squared. So I have 3 times 4 squared plus 3 times 4 plus 1. Okay, I'm going to continue on this pattern, and I'm now going to let k equal n. And if we do that, my term here would be n plus 1 cubed minus n cubed is equal to 3 times n squared plus 3 times n plus 1. So I'm now going to, I have all of these n equations, and I want to add all of them together. So I'm going to draw a big horizontal line here. And the left-hand side of all of these equations, if I add all of the terms together, what's going to end up happening is I have 2 cubed here minus 2 cubed, so that becomes 0. 3 cubed minus 3 cubed, that becomes 0, 0, 0. So what's going to end up happening is all of these terms are going to cancel out, except for I'm going to be left with this term here and this term here. So the left-hand side of my equation, when I add up all the terms together on the left-hand side, is going to leave me with n plus 1 quantity cubed minus 1 cubed. Let's see what happens on the right-hand side of my equation. So notice that if I add all of these vertically together, they all have a 3 there. So what I'm going to do is I'm just going to factor out 3. And then now what I'm doing is I'm adding all of these terms together. And if you notice, that's just the sum of the first n squares. So that's 1 squared plus 2 squared plus 3 squared plus ... all the way up to n squared. Okay, let's move on to the next vertical column. Notice that I'm adding all of these terms together and they all have a 3. So once again, I'm going to factor out 3. And then what's left over in the next column is I have 1 plus 2 plus 3 plus 4. And that is just the sum of the first n positive integers. So I have 1 plus 2 plus 3 plus ... plus up to n. And then here, if I add all of these together, that's 1 plus 1 plus 1 plus 1. Okay, so let's see if we can't simplify the right-hand side of the equation. All right, so we went ahead and we got to this point, and so now this is equal to 3 times, and notice that that is by definition how we defined it, 3 times s sub 2, and then plus 3 times, in the next set of brackets, that is just how we defined s sub 1, and then in the next set of brackets, 1 plus 1 plus 1 is how we defined s sub 0. And for 2 of these s's, we actually already have formulas for those because we found those. So let's fill those in. And for the left-hand side, I'll just rewrite this. Okay, so for the left side, I'm going to go ahead and expand n plus 1 cubed, and if I do that, that would give me n cubed plus 3n squared plus 3n plus 1, and then minus 1 cubed is just the same thing as minus 1. On the right-hand side, I have 3 times s sub 2 plus 3 times, and then the formula we had for s sub 1 was n times n plus 1 over 2. And then the formula that we had for s sub 0 was just n. Okay, let's see what we can simplify at this stage. So 1 minus 1, that's going to give us 0. I'm going to go ahead and distribute the 3 halves n into both of these terms. So that would give me 3 halves n squared plus 3 halves n. And now at this point, I'd like to get rid of the fractions. So what I'm going to do is I'm going to clear fractions by multiplying every term on both sides of the equation by 2. And if I do that, we get 2n cubed plus 6n squared plus 6n equals 6s sub 2 plus 3n squared plus 3n plus 2n. And 3n plus 2n is 5n. And notice now at this point, we have s sub 2 here, and that's the thing that we're trying to solve for. So our goal is to just isolate s sub 2. So I'm going to subtract 3n squared and subtract 5n on both sides. And if we do that, we get 2n cubed plus 3n squared plus n is equal to 6 times s sub 2. So what can we do from here? Well, I'm going to switch this to the left-hand side. So I have 6 times s sub 2. And then on the other side, I can factor out an n. So that would leave me with 2n squared plus 3n plus 1. Okay, so now I have 6 times s sub 2 is equal to n times this quadratic that we have left over in the parentheses would factor into n plus 1 times 2n plus 1. Finally, I want to solve for s sub 2. I can divide both sides by 6. And so here is the formula that we derive for s sub 2. So essentially, that is the derivation for the sum of the first n squares.